You are Nina Bazik and you work at the Metas in Switzerland. And you will present all about the sparkle. Gaël has just introduced the notion this morning, and I give you the floor for the rest.
Okay, so thank you for the introduction. Hello, everybody. I see no one, so I hope you can all hear me and see my slides very well. So my topic is sparkle and graininess, and I'm starting with this pretty slide where we have a lot of already examples of the sparkle, which is basically these tiny bright spots on darker surround. So most of you are already probably familiar with this because it has such a nice effect that it's being used more and more in many industries. We have it from the cosmetics, we have on just shiny things. You can even have a coffee that is sparkle for the extra effect. So we're dealing with this every day, but our question today is, how do we measure it? How do we deal with this texture visual effect? Okay. So now if we take first of all what exactly is sparkle and what exactly is graininess. So here we have a very simplified picture of a sparkle where we have these tiny bright spots on a darker surround. And we can only see this if we observe the sample under directional illumination. So just imagine having some sort of sample and you go outside. It's a very nice, bright, sunny day. You go outside with the sample and you can see these tiny bright spots on darker surround. And what is interesting about this effect is if you change now the angle of the sample, so if you change the illumination angle or the observation angle, these tiny bright spots actually change their location. Now, if you happen to be with the same sample outside on a cloudy day, you would observe the graininess. So on the other side, we have this granular appearance. It's only observed under diffuse illumination, and this appearance is more or less, you can imagine it as this salt and pepper kind of, let's say, noise. That's what we have in the graininess. So if you by any chance don't have a sparkle sample by your side, you can you can imagine the sparkle as if you are looking at the stars in the night. This is one kind of like similar thing. Or if you go on the sea and you see those sparkles on the sea, that's kind of the same thing. So now that we know we have sparkle, we have graininess, let's go a little bit deeper and let's look at the physics behind sparkle and graininess. So how actually we get this sparkle and graininess. So everything starts with coatings that have these effect pigments inside. So here we have again a simplification of such a coating where we have this binder. These plates are the effect pigments, and then everything is then coated on top of a substrate. Here on the right, we see a STEM image of one of these coatings, just for you to have some sort of better understanding of how it looks like actually in the real life. And okay, so this, I have to say, this is a very simplified view because you never have just a coating and these pigments inside. You always have some other stuff in the binder. You have other pigments, you have other small particles inside, so it's never as clean as this image. But we have to start from somewhere, so this is our simplified model that we're gonna work with. So what we have is we have these pigments inside, and they behave as isolated microscopic mirrors. So what does this mean? So if we take a look at just one flake, and we see how the light actually travels to the flake and back. So we have at one direction, the light impinges onto this whole coating. So we have this border between the air and the binder. It refracts, just basically according to the Snell's law that's written down here. It goes through the binder, it hits the flake, and then on the flake, the light is specularly reflected. So that means that really the incident angle is the same as the reflected angle. And this one is really measured from the, I keep losing my mouse. Okay, this one is measured really from the normal of the flake. It's reflected, it goes back to this boundary between the binder and the air, and then it goes out back into the air. So this is very basic thing, but you can see that these effect pigments really behave like microscopic mirrors. Now, if we go a bit, so look at how these mirrors actually change what we see in the end from the visual effect. Because the reflection is specular, of course, everything is geometry dependent. And geometry dependent, this means we need to be aware of how the light is incident, where we are looking at, so from which angle we're looking at, but we also need to be aware of how the effect pigments inside are actually oriented. So if they're very flat, then we have just 0, 0, and that's it. And if they're not flat, well, we can have something like this, where we have quite a big angle of the flake, and the light just goes out of the coating at a very different angle. So we need to be aware of that. The other thing that the visual effect can depend on is the size of the effect pigment. So this is, here we have 3 different sizes of this effect pigment. And we can see, so if we have a very large effect pigment, there's going to be a lot of light coming onto the pigment and then specularly reflected back out, back from the pigment. And then when the light hits the edge of the pigment, the light is not specularly reflected, but it's more or less scattered around, and it's for the purpose of this simplified model, it's basically lost in the binder. Okay, so when we go from this big effect pigment to smaller and smaller ones, so from big one we have smaller and smaller ones, we have less and less of this specular reflection from the pigment itself, and we have basically more of the scattering from the edges. So relatively speaking, it's always relatively how much of the light is scattered into the binder and how much is reflected from the pigment itself. And here we can say that the typical size range of this kind of effect pigments, it ranges from 0.5 micrometer up to 200 micrometers. And we can see here that the bigger, when the size of the pigments is bigger, we should expect to have a bigger perception of the sparkle or graininess. Okay? Another thing that we have to take into account is the flatness of the effect pigments. Of course, we're drawing them very flat, but in reality, they're not completely flat. So we need to be aware of that fact. Of course, here on my right side in the image, the non-flatness is much exaggerated. So it's never almost a half circle. It's just slight variations of the flatness. Okay, so next thing that we can that the visual effect also depends on is the type of effect pigment. So this goes more or less in line with the size as well of the pigment, because we see here we have 3 different types of this effect pigment. and we can see that the size is different. Also, the flatness is different, and more importantly, the edges are different. So some of them have very smooth edges, and some of them have really rough edges. So so this really then so this depends how much light is then scattered and lost, and how much light is really just specularly reflected from the pigment. Are you guys still hearing me? Because I'm hearing some beeps. Yes? I will assume yes. Okay.
Yes, all is
Yes.
perfect.
Okay, good. Okay, so this is one type of pigment. So one classification of pigments, and the other classification of pigments is actually from what material the pigments are made from. So we can have this metallic pigment where the light just hits the pigment and it just specularly reflects, nothing special about that. And then on the other hand, we have this special effect pigments where we more or less have 3 or more layers of different materials. And we, in the end, have a interference on the pigments itself. And that you can basically, you have this interference formula that you can calculate. And it's slightly more complex, but then in the end, you also have, let's say, more appealing effects coming out. Because, for example, if you have this metallic pigment, the only thing that you can change basically is just the lightness that's coming your way. And with the special effect pigments, then these are the ones that that can produce this coniochromatism, where the color also changes when you change the viewing or the illumination angle. And if anyone's interested, these are the thickness size ranges, the typical ones. Okay. So we are talking here about just one by one pigment, but what we're really interested in is the whole binder. Okay. So it really depends how many pigments we have in the coating. Of course, if we have just a few of these pigments, we will not have such a nice visual effect, because we will have just a few these tiny bright spots. Whereas when we have a bigger concentration, then we can have a bit better better visual effect. Okay, because we have light that is bouncing off more than just a few pigments. The other thing is the orientation of the effect pigments. Now, in the previous slide, I had all of the pigments nicely aligned, but that is never the case. That is never the reality. These pigments are always slightly unaligned, I would say, but still more or less parallel to the surface. And in the end, this is really what gives the real effect that we're looking for. So I'll talk about this in a minute. But I mean, of course, when we look at it, if we're looking at something like this, or something where the pigments are just randomly distributed, it's gonna have a really big effect on the appearance that we're getting from this effect coatings. Okay. Let me just tell you just one last thing. So when we have this kind of coating, right now I'm just talking about the pigments more or less, but when we're talking about the whole coating, of course, it depends also what the material of the binder is, what the material of the background is, and all of these things that are here in between that we are basically just ignoring at this moment. So, and now lastly, what we're seeing from this kind of effect coating, it also very, very much depends on the solid angle of illumination. Okay? So here I'm again oversimplifying. I'm just showing you one effect pigment, but if we do this for one, then we can just multiply for many, and we have the basically the biggest model. So in the end, what we're really interested in is how much luminous flux our eyes are collecting. And that we can calculate with this simple model where we just have the specular flux and then the diffuse flux. So let's go a bit deeper into that. So the diffuse one, it's really just from the binder, so from the first coating of the binder, from the substrate, from all of these particles that are still inside, from multiple reflections of the pigments and so forward. That is all taking into account in this diffuse part of our total luminous flux that we collect. Now the other part, the specular part, this one is now very dependent on this on the solid angles. So what we have here, we have the light source, and we have to know this is not a point light source, but it has its own solid angle. It's coming in under, sorry, I'm trying to find my, okay, my mouse. So it has its own solid angle, and it's coming in on the effect pigments. And then because it's specularly reflected, it goes out in more or less the same solid angle. And now, so this is the green part. And where we're looking at, it has a different solid angle. So we have this alpha 0. And now, in order for us to see one of these pigments as the sparkle, these two solid angles have to overlap. Okay, and this is what we see here with this delta, basically. Okay, so it should be slightly smaller. So just the overlapping between the green one and this beige color solid angle, wherever they overlap, that's where we see this one sparkle as sparkle. Okay, and now we can see where this distribution of the orientation of the pigments come into play. If we have this one sparkle that is in this angle, then we have another one that is slightly different angle, and then another one that is slightly different angle. We can have one solid angle, that's the green one that's coming here, then one here, and one just directly into our eye. And so the ones that have an overlap with where we're seeing, we see them, and if they're just completely somewhere else, we don't see them. And here comes this distinction now between going from the sparkle to the graininess, actually. Because when we have these small solid angles of illumination, we're limited at how many of these sparkles we're seeing, because we're limited with these reflected solid angles. Now, if we really increase this solid angle, so basically we go into this diffuse illumination scenario, then basically every effect pigment that we have inside, we're gonna see it. It's just that we're not gonna see it as much as this tiny bright spot, but we're just gonna see this salt and pepper graininess effect. Okay. Now, if anyone is interested more in the details about this whole theory, math behind this, there's a nice paper that has everything inside. And this is like a simplified model that you can actually work with. And this is another picture from the same paper, where we can see just by changing the solid angle of illumination, where we have here a very small one. It's more in the region of sparkle, and then we just keep on increasing the solid illumination until we get to the graininess part, where we really have just this salt and pepper kind of graininess appearance. Okay. So that's it from the physics point of view. Now we move on to the measurements and to how to deal with this. And it's very important to say that there are currently no standards that propose any kind of algorithms either to measure or to calculate this sparkle and graininess. And that is slight of a problem for normally, but that's when we come in. And what I want to start with is measurements using commercial instruments. So it's because there are no standards, the manufacturers can produce their own devices, and they can produce their own measurement scales and measurement protocols and everything. So at the moment we have two different companies that are making devices that can measure sparkle and graininess. Here we have a very simplified schematics of basically all four of the instruments, and we can clearly see that there are some differences between the two devices, but both can pretty much measure the same thing. All is good. There were also some studies how good this sparkle and grades actually compare with the visual experiments, and it was found that it's pretty good. So that shouldn't be a problem. But what is a problem is that if you have instrument A, the grades are not compatible with the grades from the instrument B, and that is quite a huge problem. It's also these grades, they are not clearly defined, so they're not open source for everyone to go and use them. You need to have the device, you need to measure with the device, and then you have that grade. One of the biggest problems is also this is not traceable to any international standards because it's not open source. So it's a bit of a problem because you either have the device or you don't. Let's say you don't measure the spark or graininess. Let's say it like this. So this is not good. So what we do is we need to come up with measurements that are open, that everybody can read about them, and we need to do the measurement scale so that everybody can have some sort of scale to compare this with the visual experiment, basically in the end.